Hello, so I will present CAML roots library. It's an attempt at making a safer FFI for OCaml. So I will start with a bit of context. Why did I need a safer FFI to begin with? Then we will look at the existing one and what we can do to improve it. So it all started when I tried to bind OCaml and the Qt library. So OCaml is a functional programming language that you know well, and Qt is it's a library, it's a framework for abstracting platforms, operating systems in C. And its most useful feature is making cross-platform user interfaces. So this is a sample, it's a Qt tutorial that was translated to OCaml. If we look at the property of both projects, so OCaml is a functional programming language. The representation of values is imposed by the runtime. So it means that you cannot choose exactly how, which bytes will be used for what. It is imposed by the language, and you have to adapt to this representation. And last, it's use an automatic management of the memory, a garbage collector. OCaml is a functional programming language. You have to adapt to the representation of values used by the OCaml runtime. And in exchange, it provides automatic memory management. And it means that as a programmer, you are not used to thinking about when a value is allocated and when a value is released. On the other hand, Qt is a C++ framework written in a heavily object-oriented style. In Qt, you manipulate a graph of mutable objects. So you create nodes, and you connect them. So if we look at the previous slide, yes, this application, it will be one object for the window, one object for the table, one object for the various tabs here, and all these objects will be interconnected. And this is how you define an application in Qt. And it means that the lifetimes of these objects will be very complex. You cannot compute it statically. So depending on what happens at runtime, some objects might be released or not. Also, it relies a lot on a higher order control flow. So it means that at some point, the control is passed to the Qt application, and it will invoke OCaml code at some point in the future when an event happens, for instance. And then this event might call again into Qt. So you have an intricate control flow going back and forth between OCaml and C++. On top of that, you can add concurrency. So you might want that while you are doing OCaml computation, the C++ UI is still responsive. So both threads might run on the side, and at some point they will exchange messages. And last but not least, the API is huge. So you have thousands of methods, and it changes over different versions of Qt. So for all these reasons, first a small demo. So I have a video for that. Can you see it?
T'as branché une clé USB sur mon ordinateur.
Oui.
C'est pas grave parce que ça me posait la question. Oui.
Ah.
Les gars, il faut faire gaffe à ça. Ok. Oui, non, mais t'as raison.
Désolé.
Je te fais confiance, ok?
So this is a short recording of both working together. So I started the OCaml top level. I loaded the library. So this is connecting LWT and Qt. So we will use LWT to schedule the concurrency between OCaml and Qt. And now I am starting to create a few widgets. So these basic objects. Here I am displaying the window. You assume there is a window there. And here I add a button inside the window. I give a text to the button, and when I click it, I want that an OCaml callback, an OCaml function to be invoked when I click on the button. So here, for instance, I print some messages, and when I click, when I click, the messages got displayed there. So we have here Qt and OCaml, which are working simultaneously and exchanging messages. And to get there, here is the architecture of the binding so that we can do that. So at a very high level, we use a DSL that describes the Qt library. So in this DSL, you will describe each objects of the hierarchy of classes that Qt provides. You will describe their methods, the events. You will also give some information about the retention of values. So that's how we can make it safe to allocate and release OCaml and Qt values. So from this description, we have a compiler that will produce two outputs. So this is a C++ file that will transform the Qt ABI to something which is compatible with OCaml ABI, and an ML file which will reflect all the functions we described in the DSL to OCaml libraries and programs. And on this side, we have all the support libraries that we use to enable that. So this is C code. First, there is the OCaml FFI at the lowest level. The library I'm going to talk about is camel root, which is a first layer of abstraction on top of the OCaml FFI. Then you have the Qt library. It's a C++ shared object that you have to link to. And the Qt support is basically the runtime we use to compile all the high-level functionalities of Qt in a camel-compatible way. And the colors reflect how the files are produced. So green one is what we get from the environment. This is what was manually written and what has to be updated for new versions of Qt. And the purple one is the generated code. And today we will talk about camel root. So the OCaml FFI is very efficient. So there is sundial SML, which is a numeric solver, which is implemented in C. And the /ml is an OCaml binding of this, which uses OCaml function to describe the numerical function you want to approximate or optimize. It is very expressive, so all features of the language almost are reflected in the C API. You can build and deconstruct values. You can act on the control flow, so invoke callback. And you can also raise exceptions, catch exceptions. So basically, all the control operations you can do from the OCaml programming language, you have something similar in the C API to reflect them. However, it is very low level and hard to use correctly. That is, it is easy to make mistake when you manipulate the library, especially if lifetimes are involved. And it is risky. If you make a mistake when using the library, it won't show immediately. So at some point later, during the execution, you might have a corruption of the heap, and it will crash the program in a totally unrelated place. And because of the hard-to-predict nature of the GC, it might work most of the time, and if you are unlucky, it will crash for one invocation. And to understand how this works, we have to look at the representation of values in OCaml. So there are two important concepts, the words and the blocks. The words is basically just an integer which is the same size as a pointer of the host platform. So 32 or 64 bits in most cases. If the least significant bit of this value is 0, then it is actually interpreted as a pointer, as the address of some chunk of memory. If the least significant bit is 1, then the remaining bits are interpreted as, most of the time as a signed integer, but really the GC will not make any assumption about what they mean. So you have 31 or 63 bits free. And in the CFFI, it is represented as this type. So it's an alias to an integer which has the same size as a pointer. And the second concept is a block. So a block is a chunk of memory which is managed by the GC. its size expressed as a number of words, so a multiple of the size of a pointer, is stored in a header which is just before the beginning of the block. And this header is used to determine whether the block should be scanned or not. If it is not scanned, then the GC will just ignore its content, and you are free to give it the interpretation you want. But if it should be scanned, then all the remaining words are interpreted as pointer to other blocks or integers. So this is the recursive nature of OCaml values, which enable to represent all the construction from the higher level language. And in the C FFI, this is reflected by, for immediate values, an API which looks like this. So we are turning a long integer from C to an OCaml value. So essentially, this will shift the integer by 1 bit and set the least significant bit to 1. And in the other direction, this will just shift right to reconstruct the original integer with the most significant bit lost. And for Boolean values, you have a similar function. More interestingly, for blocks, you have this function. So OCaml alloc function will take the size of the block as a number of words and the tag. Basically, it's the tag which determines whether the block should be scanned or not. But it doesn't really matter for this. And the field and store field functions, they will just read the nth word from the block and mutate the nth word from the block. So with these three functions, you can allocate a block, read one field, and set one field of this block. And it would be very easy if we just had to deal with that, but periodically, the GC has to do its job. And for that, it needs to traverse the whole heap, and so it needs to know which OCaml values are maintained alive by the C code. And in some circumstances, it will decide to copy and compact these blocks. So it also needs to be able to update the C values. So for this, it needs to be sure there is no alias that it is not aware of on the C side. Let's look at a very simple example. So we want to build a pair. So we have two values and we want to return a pair, which is a tuple of these two values. So it's expressed as one line of OCaml, and on the C side, it looks like this. So we have a primitive which is called CMK pair. It returns a value, so this is the type of OCaml values, and takes two other values as argument. The first interesting thing is this macro call. So basically, this will set up a set of roots, which is the list of values the GC needs to traverse if it needs to do its job. So with this macro, we add the addresses of x and y values to the set of roots. With this second macro call, we declare a local variable, which is called result, and adds it to the same set of roots. Then it's pretty normal code. So we invoke the camel alloc function, which will allocate a blocks of size 2. So this will be the blocks that will receive our tuple. Then we store the two fields, and finally we return the result. And this macro will remove the set of roots. So basically the jobs of this syntactic sugar from the OCaml FFI is to create a new set of roots, register addresses to OCaml values in this set of roots, and remove the set of roots at the end of the function call. And now to see how easy it is to make mistake. Here we would like to compose calls to our previous function. So to make nested pairs, it seems that we could simply call the same function multiple times. But the problem here is that after the return of the first call, we have an OCaml value which has not been registered in a root. So if the GC triggers in the second call, then this value might get erased, and you will get a heap corruption. So this is a problem. The first result is not stored, and the second call might corrupt the heap.
Yeah, but it's even worse, right? Because you might end up freeing it twice. So you have two problems.
Freeing.
Can you repeat the question for the mic?
It's okay. No, it's okay because it's managed by OCaml.
Yeah, yes,
no,
yes.
that's right. No, because I thought there was another problem that, in fact, the result you unregistered twice potentially. And that could, I don't know if that creates a problem, but yeah, so there are really two problems.
No, it's not
registration
registered.
and potentially the CAML result doesn't register the for registration there.
Well, I don't.
CAML param 4. You're
Yes.
registering those roots because
Yes.
let's say in garbage collection terms
Yes.
what they are, roots. Then you call the make pair with X and Y, which is register again roots
No,
for
it's
X
not.
and Y.
Oh, yes, but these roots will be removed at the return of this
I know.
function.
Yeah, that's correct. So they are, okay, fine, thank you.
Okay, so that's one way to misuse the API. There is another slightly more subtle way. So there is still a bug in this code. Here what happens is that when we make the call to MK pair, the outer one, the C compiler might load the X value. And then it will call the second function. And if the GC triggers here, the X value is registered in a root, but not the copy it has made on the stack to invoke the second call. So more precisely, what happens here is that the same value is read and written in the same sequence point from the C compiler point of view. This is an undefined behavior. So this code will result in similar bugs from the previous function. And so what we would like to do is to detect when a root has not been registered properly, to prevent these undefined behaviors by restricting the kind of code we can write, and to simplify the management of roots. And so for this, we provide an API which is centered on roots, focusing on roots. The problem we had before is because the OCaml values does not behave like normal values from the point of view of C. Because their address is captured by the GC API, their value can change at any time. and so they won't behave like what a C programmer might expect. So passing an argument is not just copying a value, but actually there is some loading which is hidden there, because normally with a C variable it would have been stored in a register, whereas here, because the C compiler knows that the address has been captured, every time you read the variable, it has to reload it from memory. And so what we propose for this is to, instead of passing values as argument, we pass the address of the roots as argument. So this way, we can control when the dereferencement, the actual loading from the memory, will happen. So in Rust, there is a prototype which is called camel oxide, which shows that the Rust type system is actually powerful enough to capture this distinction between values and roots. And so when you read a value with this binding to the OCaml FFI, it gets a different lifetime from the variable in which it is stored. In C, we cannot do that. So what we propose in this library is to replace all arguments of type value by arguments of type value star. And the address of the root is stable. So even if the GC changes the value which is stored at this address, we won't have a problem. And we cannot have return values with this style. So what we do instead is to pass one more argument, another root in which the result will be stored. So the API has to be rewritten in a kind of destination passing style. Because the return type is void, it's unlikely that the user will nest the calls. So the style is a bit more verbose. but we can prevent the erroneous use. And here, for instance, we see that if we wanted to mix both style of API, we would have to take the address of a temporary, which is returned there, because this returns an OCaml value, whereas our API expects a root. So this also cannot happen. In the end, the code starts to look like administrative normal form. What that means is that you are only passing values to the functions, and you have a very sequential code. Like every call has to be on its own line. You cannot nest calls, and you have to be very explicit about the memory management. So it's slightly more verbose, but the possible mistakes are prevented. And there is even something more we get out of this. Since now all the arguments are pointers, the dereferencement, which happened implicitly when we were loading a value, now has to be explicit, but it doesn't have to happen in the user code, only in the primitives of the FFI. So nobody should ever put a star in front of a root. It's only the library from the functions from the GC library which needs to actually read inside a pointer, inside a root. And because these pointers should be registered, because these pointers are root, they should be registered to the GC. So now we can provide a defensive mode, which can be switched on during test, which before every access to a root will check whether it is actually registered or not. So we have an alternative implementation of the API, which can check that every access to a root was actually done through correct manipulation of the API. So with this, we can prevent the undefined behaviors. We get a defensive mode which can detect at runtime the mistakes. We have something which is slightly more verbose, but with a similar performance profile. And so this library offers just a small layer that sits on top of the OCaml FFI that makes something safer. Here is the Qt bindings, and here just the camel root part. There is slightly more in the implementation, so it actually works well with C++, so there are some facilities for using C++. And we also allow to dynamically allocate the roots so that you don't have to pre-allocate them, and it also enables a slightly more dynamic kind of code where you don't know all the roots you will need inside the binding. Compared to the existing work, there is OSAFire, which is a bindings verifier. It worked well 10 years ago, but I have not been able to make it work with something more recent. There is C-types, which solve a slightly different problems. Here you write the bindings using an embedded DSL in OCaml, and it will either use libFFI to dynamically make the calls or generate some C source that will be more efficient. And camel oxide is this proof of concept I showed before, which using the REST type system can enforce the GC invariants. And just some performance measure. So this is the implementation of the pair function using the normal OCaml FFI. This one uses a slightly slower call. So basically here we bypass the GC checks because we know we are using the API in a certain way that is safe. So this is the fastest implementation you can make. This would be the normal implementation if you follow all the rules of the CFFI. This is using our abstraction, and this is using our abstraction with the safety checks enabled. And there is a slight overhead, and it is because these ones are implemented using macros, whereas this is a function call in a different C objects. So if you really need performance, you can inline this and recover a similar behavior. But we just wanted to make sure that the overhead is not prohibitive in average case. And that's all. Thank you.
Thank you.
So the benchmarks you show are a bit scary. It looks like, wow, this is twice as slow.
Yes.
But of course, these are twice of a very fast thing. So my
Yes.
question is, have you tried on a real project that uses the CFFI lag, for example, the SunDials people,
No.
to use your library and see that it doesn't actually make any difference?
No, not yet. I really just wanted the worst case to be quite predictable, and I didn't really try to optimize anything.
So in terms of C-types, because we've used C-types in the past, I understand that obviously here you have to write more code,
Yes.
but you should get a little bit more performance. Do you have an idea of what's the difference? Have you done any test?
So it's
And
not
again,
really...
dynamic access, so without generating the stubs, the C-type stubs.
No, I don't have any idea about the
Not even
overhead.
okay.
But in my case, C-types was really not appropriate for binding C++ code. So there are different reasons. The concurrency, the lifetime management, and the fact that we are calling to C++ all made C-type not quite fit for this case.
Just a clarification. At some point in the context of C++, you mentioned region. So did you mean that you can allocate OCaml object using placement new operator in C++? And then provide those routes to the garbage collector? Because that would be quite interesting.
So no, I cannot do that. Well, I didn't need to do that. So
Okay.
I didn't do that. In the kind of interesting interaction between C++ and OCaml, what I can do is allocate C++ values in minor heap. So
Okay.
Qt provide enough introspection that you can know whether a value can be moved or not. And if a value can be moved, then I instruct the...
Because I don't know if you've thought about this, but I've worked in the past on languages in which there was a concept of region that you can manipulate. And the advantage of that is that sometimes, and then you have to be careful on who can reference to who. So we get into right barriers, yeah. But if I can allocate with placement new, and if I can tell, based on my code, when I'm done, all of a sudden, there is an entire region.
So it's possible to do this. Actually, I use regions and the RAII idiom to automatically free them. With the placement you can do something slightly different, which would be if you don't mind manipulating slightly larger values, you can actually not abstract the OCaml values, but the OCaml root representation. And so your basic OCaml, C++ value would be a valid root as from the point of view of the GC. And so the placement operator would update the address of the root. And when leaving the scope, you would unregister the root from the garbage collector. So this is the kind of implementation I envisioned. The problem is that the minimum size of the root registration is 5 or 6 times bigger than an OCaml value. So just using a pool and RAII was good enough for me, and I didn't go further.
Encore des questions? On remercie Frédéric encore une fois.
Thank you.